last time we took those vehicles, solar structure, that worked out really well. Because their side wasn't necessarily.
All right, good morning, everybody. Good morning. Let's try it again. Good morning, everybody. Good morning. Excellent, excellent. We're here nice and bright and early to start the spring 2016 edition of our senior presentations. We've got a full day of knowledge planned for you. Hopefully you'll stay all day. If not, I'm sure that the pieces that you do see, you'll be very impressed with. The students have worked very hard this past semester, and this is the culmination of their engineering education. They may have a final or two left, but this is really where they can show you what they've learned over the course of their education. So with that, I am going to let Dr. Ron Gersing introduce our first team. And they're excited about being the first team.
So Dr. Mitchell mentioned this being the culmination of their education, and in this case, it kind of is, well, it always is, but this especially so because this is a project that they saw a need for from multiple years of competing with the IEEE robot and seeing, the need for some kind of a base robot to allow people to start early on. And so Richard, Alejandro, and Charlie are going to tell you.
Good morning. I am Richard Schuler. This is Alejandro Medina Juliak and Charlie Northerner. And our project is the IEEE modular base. The purpose of this project was to design a modular base for the IEEE Southeast Con Robotics Competition. It has been noticed through previous competitions that the size of the robot tends to be the same for all 5 years. It actually confirmed that next year the robot is to be constrained by the same size. So seeing this trend, a need for a modular base was needed. For this year's competition, it simulates a shipyard's logistics system. Shipping containers had to be picked up and sorted by size and color and deposited in the rail cars, boating system, and trucks to be shipped. Robots must be autonomous, and the size has to be constrained to a 1 foot cube.
The project goals for our project include the creation of a 1 foot square modular base with easy and very user-friendly programmable functions for both movement and I2C communication. Similarly, preliminary velocity control and integrated motor driver design will also be created so that the following IEEE groups will be able to work with it. We selected 3 different drive types for our design, which are omnidirectional, directional, and inline drive. Each one of these has different advantages and different disadvantages, which allow the future IEEE groups to select in between these ones depending on what the specific competition requires. For this year's competition, we selected the omnidirectional drive because it allowed us to move on sideways without the need of the robot to turn from clockwise or counterclockwise. It allows the robot to move just by setting, as you can see in the image, just by setting the direction of the rotation of each wheel. Depending on how you select this rotation, the robot will move left, right, backwards, forwards, or turn. Here are the 2 base plate designs that we created. As you can see, the omnidirectional base is the 4-wheel setup, which is right here. We created motor bracket mounting holes for both of our plates, as well as holes for water management. The material provided to us was a 1/8 inch aluminum sheet alloy 6061. However, in order to ensure that this material would withhold the loading that future competitions might need, we proceeded to create simulation in using SolidWorks software. While creating a simulation, we applied a 45-pound force load on the base, and we achieved maximum combined load stress, as we can see here, of about 13.5 meganewtons per meter squared. For 1/8 inch 6061 aluminum of one permanent deformation occurs at around 55 meganewtons per meter squared, which, as we can see, it's not even 13.5 is not close to 55.15, which means that our design meets our requirements. The same thing happened with the 3-wheel setup, where we had a 45-pound force load, just as like in the previous slide, and we had a small increment of the maximum combined stress of 13.6, but still it's not close to the same 55.15 meganewtons per meter squared. In order to achieve our design, we needed to select our components. This involved the selection of motors, which is right here. We selected a motor drive, the DC motors, and motor drivers, which allow us to input the right amount of volt current in the motors that would also allow us to be able to control the motor. Similarly, we selected our omnidirectional wheels, as I previously mentioned, and our distance sensors, which are right here, which pretty much allows us to know where the robot is located inside the actual core. Here we have another layout of the component connection. We have the 4 motor drivers, which each one individually controls and provides the current to all the 4 different motors, in this case for the 4-wheel setup. And all of them are connected to the microcontroller, which itself is connected to the 2 sonar sensors or distance sensors that again allows us to know where the robot is located at.
So the brain of our robot is the FreeSoc 2 microcontroller. The FreeSoc 2 microcontroller is a SparkFun version of the PSOC 5LP. PSOC means a programmable system on a chip. So we were able to program all 72 general purpose input and output pins to any specification that we needed for this robot. After the microcontroller was chosen, sensors were needed to help with the navigation for the robot. The sensors we decided to go with were the time of flight, or the TOF rangefinder, for its range from 0 to 4 inches. We wanted a shorter distance sensor so that we could detect smaller objects, such as for this patch competition, to pick up the blocks to be sorted. We also went with the HC SLR4 ultrasonic sensor for its range in longer distances, from a range of 0.5 to 78 inches. We used this to determine where we were on the course at all times. How the ultrasonic sensor works is we set a trigger pin to high, and then we delay for 10 microseconds. During that delay, we then set the trigger to low, and we begin to wait for the echo of the sonar pulse that we sent. We then start, after we receive the first pulse, we then start a timer. Then we stop the timer once we stop receiving the echo of the pulse back. And we put this into the equation given to us by the data sheet, which is the distance in inches is equal to time divided by 148. This was a conversion factor given by the data sheet so that we can convert the speed of sound in air to a distance in inches. So here's a diagram of the timing that we used for the sonic sensor, ultrasonic sensor. As you can see, we triggered a 10 microsecond input pulse, and then the sensor itself sent 8 sonic bursts out, and then we wait for the echo to return, and we measure that time it takes for the echo to come back to it. So for the motors, we chose these motors for their high speed and their high torque capabilities. So our motor specifications at 12 volts is we had a max speed of 350 RPM, a max torque of 110 ounce-inches, and we also had a no-load current of 300 milliamps, a stall current of 5 amps, and a built-in quadrature encoder. With this quadrature encoder, we were able to detect the rotation of the motor shaft. So as you can, ours was a Hall effect sensor. So as you can tell in the figure provided, As the red magnet approaches the blue box, which is a transducer, it induces a high voltage that sends to our microcontroller. Our microcontroller sees these as shifts, so then we were able to tell how many if their motor shaft rotated. Because of our Hall effect sensors, we had 2 phases shifted by 90 degrees, which allowed for 1,920 pulses per full revolution of the motor shaft. So to run our motors, we need a motor driver. Our motor driver specifications, it supports a motor input of 4.5 to 13.5 volts, which matches our motor input of 12 volts. And then the motor driver also has the capability to run 2 separate 1 amp channels, which allows us to continuously output to 2 motors 1 amp per channel, and it has a max current output of 3 amps per channel. So then we needed to write movement functions once we implemented all these sensors together. So we wrote movement functions for forward, reverse, left translation, right translation, turn left, turn right, and soft brake. So what we did is the user inputs a speed, an encoder value, and a direction that they wish to turn. And then our code sets the motors to that encoder value and direction and speed. And then we wait for the encoder value. We continue the motors until the encoder value that the user set is reached. The next slide shows us a little bit of movement that we had for our project. Here you can see we had a forward movement, and then I had a left strafing code written in it as well.
In order to communicate between these components, more particularly the microcontroller and the time-of-flight rangefinder, we decided to go with the I2C communication method. This method consists of a master and slave device, and the master being the microcontroller and the slave being the sensor. And the master is in charge of keeping the time pulses, and the master is always the one that addresses the slave. The slave only reacts to the signal and the directions that the master is given. Here we can see how a typical I2C communication bus it begins with a start switch and the 0 bit, followed by 6 data bits, and then a read or write, depending on what the master is sending to the slave, and finalizing with an ACK or acknowledge bit, which tells the master that the bit string has been completed. This is of course just a tiny part of the I2C communication. There's several of this going in different directions, but this is just an example of how it works. In our project, we used it, as I said, between the TOF or time-of-flight rangefinder and the microcontroller.
With our movement functions programmed, we began our testing phase. And early on in this testing phase, it was realized that all 4 of our DC motors were not rotating at the same speed. To further address this issue, we recorded the encoder data for 3 full rotations at roughly half of their maximum velocity. This data was then used to calculate a speed over time for each individual motor. This data was then plotted in this figure here. As you can see, one of the 4 motors is much slower than the other 3. To further address this issue, we looked into imperfections within the DC motors themselves. As we know from electrical machines, DC motors inherently have different internal properties. This could be due to errors within the manufacturing process or internal imperfections within the materials they're made of. However, to prove that this was the case, and this is why we were having this velocity inconsistency, we went into our motor drivers to test them out to ensure that we didn't just have a bad motor driver. Upon testing, we realized that all 4 of our motor drivers in this project outputted the correct voltage for the speed condition we were sending it, proving that the motor drivers were in fact correct and were functioning properly, and that the issue was within the motors themselves. So as to how we could solve this issue, there's numerous control system methods that can be used to bring and synchronize these different motor speeds together. However, in order to do so, we would first need a way to implement this control system. Our method for doing so was to design a reprogrammable motor controller that would be able to control all 4 different motors while being able to support a program to synchronize the motor velocities. In order to hold this program, we chose the Teensy 3.2. The Teensy 3.2 is a small, compact microcontroller with 34 general-purpose GPIO pins, or input-output pins, 12 of which are pulse-width modulated pins. These pins were used to set the speed of our individual motors. Up to 21 of those pins could have been used as analog input pins, which is what we use to send our information for setting the speeds from the FreeSock, the main microcontroller, to our secondary microcontroller on our motor driver. This board is I2C compatible, so if later on in the future competition a need to send more data into the system is required, I2C can be set up to send that data. Here, you can see the prototype of this board. We wanted to first ensure that it would function correctly as we intended before we went into more extreme measures of making it able to be used for years to come. As you can tell, this only utilizes 2 of the motor drivers. In the end, we wanted to utilize 1 per motor, so that would be 4. And the wire management here is not good at all. This would cause an issue when you're handing this down from years to come, because if a wire were to become unplugged from year to year, you would then have to figure out where that wire came unplugged, reconnect it, and that could take 3 hours to a day. So what we wanted to do was we wanted to embed this in a printed circuit board, as you see here, so that as we pass this down from years to come, it's in the same state as it was from the previous year. As you can see here, we have 4 motor controller pads. The Teensy pad here, that will be our microcontroller. Pads for our communication between the 2 boards. And 4 pins for where the motors will connect. A big part of this project was we want to make sure that it was cost efficient. So what we did was we logged our time spent on this project and equated it to a cost with our bill of materials. The end cost turned out to be $2,595.43. While this seems like a lot, it's really not. Because what we're able to do is our package that we're able to deliver can be used for years to come. So if you spread this cost over 5 years and consider the fact that groups in the future are going to be able to pick up what we've done, decide what drive type they need to use, quickly modify it, and then use our pre-programmed functions to quickly be able to navigate their course in a matter of a month. In conclusion, a reusable, easily modifiable robotic base has been designed. Easy to use movement and I2C functions have been programmed and implemented and fully tested. And an easily reprogrammable, intelligent motor controller has been designed. A few recommendations. During this competition, our robot was incredibly heavy, as you can see here. The motor brackets that we purchased were not capable of correctly supporting this load. So we recommend that you fabricate your own motor brackets to be able to compensate for the heavier load that you may encounter in your competition. We recommend that you continue on with modular improvements as you go along in creating your own robots for future competitions. By doing so, you will not only be helping yourself, but you will be helping the group after you and after them. And eventually, you will have so many modular improvements that you have more time to design the actual task of the competition instead of just basic movement functions. Also, we recommend that you take use of the AEC. The AEC has machinery that allows you to create application-specific components that will allow you to correctly be able to implement custom components into your design. We would like to acknowledge a few people. We'd like to acknowledge our friends and family for helping us throughout the semester, giving us support. We'd also like to thank our faculty advisor, Dr. Deersing, for all of his help throughout the project, as well as his help with being the IEEE advisor. Dr. Mitchell, for allowing us to have this project a possibility and for funding us for our competition. The rest of the engineering faculty for assisting us in this project as well as assisting us in and out of class. The rest of the IEEE members for all of your assistance in not only our issues but also your projects as well. It was great working with you all. Chris Huber and Alex Flick for being available 24/7 to assist us in our custom part fabrication needs. And of course, Ms. Donna Moore for keeping us on track throughout the semester. Any questions?
All right, questions?
Great job, guys. My one question is related to the ultrasonic sensor. Would there be any chance of picking up air on the whole course using that sensor, or is it like a linear shot to pick up your distance?
It is a linear shot, so it shouldn't, nothing in the air should affect it. It's just a linear shot and it bounces off an object.
Thank you.
Hi guys, really nice job. I just have one question. What drove you in the direction of four-wheel drive? It seems kind of complicated. I was wondering if you considered two-wheel drive at all.
The reason why we selected four-wheel drive was basically because we needed to, for the robot to move sideways, because we needed it to pick up the blocks, which were displayed in that way. So this was the easiest way for us because we could actually move sideways without necessarily having to turn clockwise or counterclockwise, and we could just set up our motor directions, which would allow us to move sideways.
Yeah, I also have a question regarding the ultrasonic sensor. Did that system use an interrupt-driven edge detector, or were you polling that pin?
I think for the sensor, we're pulling for it.
And with regard to your wheels and your encoders, how do you account for slippage of the wheels?
So how we, for the slippage of the wheels, that's why we used the ultrasonic sensor along with the encoders, because we knew that the encoders would just tell us rotations of the motor shaft. So of course theoretically you could spin out and it would know it would go that distance. So for our movement functions, we used a sonar, we used two sonars in the front that helped us reiterate that we made it that far that we told it to go.
Thank you.
Other questions?
You guys didn't really talk much about how much coding you had to do, in what areas, how many lines of code or whatever that had to put into this.
If we count our individual function calls and some of the other code we've written, it was upwards of over 5,000 lines of code that we had to write for this project.
Other questions? All right, you've got, on one of your slides, you indicated that you wanted to have a soft braking capability. What was that for?
So we did the soft braking capability because we noticed that with the wheels, the Mecan wheels we chose, whenever we did a hard brake, they seemed to shift because there's rollers on the bottom, so that shifted one way or the other whenever we did a hard stop. So we decided to do the soft stop to allow for the motors to slowly stop, which didn't cause that left and right movement whenever we came to a hard stop.
Okay. Was there a corollary to that for acceleration? Did you get any jerkiness in acceleration? And would a soft acceleration also be something that you might want to have in this
soft acceleration wasn't considered. We didn't see an exceptional need for it. The translation that we saw at the end with the braking did not really occur with the acceleration. However, it could have possibly helped, but we just didn't consider it.
Okay, thank you. Any other questions? All right, let's give them a hand.